Okay, we are streaming live. It is April 9th, Friday, and I am arriving in class here shortly. Dropping into game April 9th, Friday. CS-030, Westmont College. Here we go. Okay, double broadcasting right now. Good morning, everyone. See everyone rendering in. I'm going to shift over to single broadcast in YouTube and we can run through our checklist. Shifting to single broadcast in YouTube. Okay, let's see. Can I get confirmation that audio and streaming is working okay by having someone in the class enter into chat? Something to that effect. And, well, great, thank you. All right, so let's run through our checklist. Make sure we're good to go. Make sure you got your VPN activated. I had to drop out because I forgot to turn mine on, so we can do audio in game. Make sure you've got a quiet location and/or tell your roommates that you are in class, and if they refuse to listen to you, throw a mug at them. Turn off notifications on your phone or computer. So that means notifications for me, do not disturb mode on my computer, and turn off notifications on my phone so that I don't get updates about Harry and Meghan's movements near me. Put on your headphones, shut down any extra apps or browser tabs that you might have open. In my case, how am I doing? I think I shut everything down that I expected to have down. Yep, I am good to go. All right. Open Canvas, we'll take a look at that in a second. Open Eclipse and connect to Saros. We're going to be firing up some code today. And I see a few of you have already checked in. That's great. And I will add other people as I see them show up. Just double checking that. Okay. Working on Saros. Make sure you got Firestorm open if you don't have it open already, and if you are for some reason can't get Firestorm working, I prefer you did that, but leave a message in the live chat on the YouTube stream. I see Ben Fernberg is there right now. All right, hi Ben. Other people in class. Let's see who we got in class right now as we finish up our checklist. I got Ethan, good morning. Trent, good morning. Sam, good morning. Dee Dee up front. Oh, we haven't gotten to baking our avatar. So let's rebake our avatars. Avatar health, force appearance update, and then world, environment, midday. So it looks like we're at the same time. Make sure your draw distance is set to something low so you don't have too much lag. I'm at 176. And check in on the attendance machine if you haven't checked in on the attendance machine. So Dee Dee, good morning. Good morning, Thomas. Good morning, Josh. Good morning, Landon. Good morning, Faith and Carson. Good morning, Matthew. Good morning, Ben. Good morning, Morgan. Good morning, Ben D. Good morning, Monty. Okay, great. Did what just drop out? The YouTube? I see your chat. It looks like it's streaming okay on my side. I still have good streaming. Let's give it a second and see if it resolves. Looks okay to me. Could be, it says it's a loading error, huh? Let me go into Inception here and see what I get. Oh, huh. Okay, I see what's going. I see the error. Let me see if I can adjust it. Hmm. How's that? Inception mode. Do, 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 do. Working now. Okay. All right. Out of Inception, double broadcasting, going back to YouTube single broadcast. All right. I'm in YouTube single broadcast. All right. So let's take a look at. We went through our checklist. So checklist is good. So I'm gonna. Last thing being check in on the attendance machine if you haven't already. Okay. I'm gonna shut down my checklist there. Give me a few more CPUs. Let's take a look at the attendance here. So today is April 9th. We'll look at that in Canvas in a sec. Actually, let's look at it in Canvas right now. Let me get a Canvas window up. All right, broadcasting the Canvas window. This is our class right here. Today is April 9th, Friday. It is Friday because that's what a Friday is. It's Friday. We are in section 2 of 3 parts of chapter 13. The first part was Dr. Lee's lecture in the UN room. Today we're going to do a second lecture on recursion, and then Monday we're going to do an alternate kind of class. So as we look at this in game on the board, it says chapter 1 started. It says chapter 13. Part 1, Dr. Lee started this chapter. Part 2 is today, which is backtracking from the textbook, section 13.6. And part 3 is going to be Monday, in which we're going to do a Sudoku lab, which is we're going to write a Sudoku solver. All right, and so as we look at what's going on here, on Monday you have the first drone challenge due, and in class we're going to have a workshop. So you're actually going to end up having 2 things due on Monday, but one thing you should be able to do in class. The drone challenge, we'll start looking at that in a moment. All right, let me bring up our Canvas board for today. My window's just moved around. I'm looking for my Canvas window. I have my Canvas window. Here it is. Okay. So here's Canvas for today. It is published. I will drop the link in game if you have trouble navigating to get there in Canvas proper. Okay. All right, so let me just open us in a word of prayer for a sec here. I'm going to read a prayer that I got on my wall here. It's just sort of a kind of a liturgy for the day. Let me see if I can pull it off without ripping my mic off. We're getting to the end of the semester. I am grateful for the way we've been able to hold it together. I know it's been a struggle. A lot of you are facing a lot more challenges than you would otherwise if it weren't for the pandemic. It's reflected in various kinds of things, but as a community, I think we have been remarkably resilient. We haven't come out unbattered, but we are coming out okay, and that's pretty good considering what everything we have been through. So I'm going to read a prayer. It'll take about 2 minutes. It is just kind of a daily prayer I've got on my wall to help, I guess, give me perspective for the day. So I'm going to read it for us. O Lord, grant me to greet the coming day in peace. Help me in all things to rely upon your holy will. In every hour of the day, reveal your will to me. Bless my dealings with all who surround me. Teach me to treat all that comes to me throughout the day with peace of soul and with firm conviction that your will governs all. In all my deeds and words, guide my heart, my thoughts and feelings, and in unforeseen events, let me not forget that all are redeemed by you. Teach me to act firmly and wisely, without embittering and embarrassing others. Give me strength to bear the fatigue of the coming day with all that it shall bring. Direct my will, teach me to pray, and you yourself pray in me. To the glory of the Father, and of the Son, and of the Holy Spirit, now and ever, and unto ages of ages. Amen. All right, great. Good. Thank you. All right, so let me get started to see if anyone has any logistics questions or any other things they want to touch base on before we get rolling. All right, not hearing any questions at the moment. Feel free to throw them in chat as they come up, and I can hit them asynchronously as I get a pause. So what I want to start with is now, given that you have had an opportunity to absorb some of the drone world stuff that we talked about last class, maybe some of you have had a chance to work on it a little bit. What I would like to do is just revisit the sample code that I gave you and kind of walk through it a bit so that you can, I don't know, now with a little bit more background, you might be able to absorb it a little bit better. So let me bring that up. What I want to do is create a new Eclipse window. New window. There it is. And I'm going to put that on the screen. And I'm currently not going to be using Saros for this bit. So as you're getting set up in Saros, this is not what I'm talking about right now, but I'll go ahead and add a few folks to that. All right. As you are doing that, let's take a look at the drone world. All right, so now we've looked at drone world once. Now we're going back into drone world and we see a couple things. We see that this is a Maven project. Just as a reminder, Maven is a way of managing remote libraries. It's a way of putting a configuration file into your Java project so that your Java project doesn't have to have all the libraries that you depend on. You just have to announce which libraries you need. And when you update your project with Maven, Maven will go out and download the libraries that you need and will put them in a location on your computer, on your hard drive. On my computer, it goes under my home directory and in a directory called .m2, and that's usually a hidden directory, so it's hard to find it. But you can see, at least in my Eclipse, you can see where it's placed by looking at the grayed out text next to one of the Maven dependencies, and it'll list the full file name to the right of where it's stored. And you can see that after I have right-clicked on the top of the project and gone to Maven and done Update Project, all of these libraries, and go through the wizard, all these libraries should be downloaded fresh, and I actually have them on my computer, but they're not going to be in the directory where I stored Drone World. They're going to be in the Maven directory because other projects that are also Maven projects that also include the same libraries will share the library so that you're not downloading lots and lots of copies of a library if just because different projects are using the same one. So that's another advantage of Maven. Okay, so that's there. You may have other libraries in your computer that are local that are in the file system. This is one for parts 2 and part 3 that you don't have that one yet. You'll have an assets directory where you have some of the graphics that we're using. For example, the models of the drones are in there, the graphical models. And there's the pom.xml, which includes the Maven instructions in it. As we open the SRC directory, SRC stands for source, as in source code. It's an abbreviation that comes from the Linux operating system. You can see that there's a variety of different packages here. This is how I, when I wrote the software, organized all of the different software that's present. And you can see I broke two pieces down into the simulator, into the visualization, and then I have this reference package, which is also a directory. And in that, I put the code that students are supposed to work with primarily. The main one that you're working with, or the controller for the simulation, is sometimes helpful. So if you go under My Simulation Controller, you'll see a bunch of constants here that the simulator references when it runs the simulator. And by setting these in appropriate ways, in particular, you usually don't have to deal with any of the ones under random. The rest are just getters and setters. But at the top, you can set different kind of components to it. And so, for example, if you set same random numbers each time to true, that means each time the simulator runs, it will randomly put the ninjas out and about, but it's going to put them in the same random location every time you run it. That random location is dictated by this number here. So every time you run it, the ninjas will be in a particular random location. If you change this number to like 26, the ninjas will all end up in a different location, but as long as you have same random numbers each time set to true and the random number seed set to 26, they're going to be in the same random number place over and over and over again. That's really helpful for trying to develop some software because you don't want the movement of the ninjas confusing your software development. You would like to be able to come up with a plan for how your drones are going to move around the world and develop that plan with the ninjas staying in one place. And then later on, you can change this same random numbers each time to false and see if your algorithm still works when it's run under the testing condition. When I run it for evaluation and when we run it for a competition, you will not get the same random numbers each time. They will be actually randomly generated. High resolution set to false will make you have little boxes instead of fancy drones, and that'll just run the program faster, which is nice when you're doing it quickly, when you're doing lots of iterations. Drone model count equals 1 means that you're going to load up less assets at the beginning. That'll keep it a little faster. Simulator speed you can set to anywhere from 1 to 100, 1 being slow, 100 being fast. It's not necessarily the case that you want it running at 100. By default, it comes to you at this setting of 20, and that's so that you kind of can follow what's happening without things like zipping around too fast. And you probably, while doing development, want to set quarantine drones equal to false so that if you set a debug breakpoint in your drone code and you take more than 10 seconds to examine your code, the simulator isn't going to shut down your drone because the simulator doesn't know whether your drone is not responding because it's paused by the debugger or whether it's not responding because it's in an infinite loop. Since either of those things could be true, if quarantine is set to true, the simulator will shut down your drone, put it into quarantine, even though it's not causing a problem, you're just debugging it. So I'll set it equal to false for the moment. Any questions about those settings before I look at the skeleton controller that I gave you? Okay, that's a good question. So the question is, the rubric talks about real world seconds and having to deliver ninjas in a certain amount of time. If I said real world seconds, that's probably not a good way to describe it. I actually mean in-game seconds. So if you speed up the simulator, it's just going to make the seconds in the game roll faster, but it's not going to change the same amount of, like, let's say that you have an algorithm that delivers all of the ninjas in by time tick 5 million in game. If you set the speed to 1, going from 0 to 5 million is going to take a long time. If you set the simulator speed to 100, going from 0 to 5 million is going to happen much faster. But all the same work is going to happen. It's just going to either be visualized faster or visualized slower. So when I talk about the rubric, what I'm talking about is that in-game time tick. And so it doesn't matter what the simulator speed is with respect to that timing frame, because you're just, does that make sense? Yeah, okay, good. That's a good question. Any other questions? Okay. All right, so let's take a look at the drone controller skeleton and just walk through it now. All right, so it is a class called My Drone Controller. It has to be called that because the simulator is going to create one of these and it needs to find the right name. It inherits everything from drone controller skeleton. So, and I place that there in reference to if you're interested in looking at all the possible methods that you could override. In the example here, I created a method that returns a random number, and the way that this works is it's using the central random number provided by the simulator so that those constants, same random numbers each time, and the random number seed so that they matter. Like you could in your code make your own random number generator that doesn't care about those constants. And then you'll get random numbers every time, whether you like it or not, regardless of what that constant is. But if you get random numbers this way, it's going to respect the constants that are in the simulation controller. So that's why that's there. Okay, get next drone name is a way for you to, is the way that the simulator asks your drone company what you would like to name your drones. And this is kind of immaterial, it's just fun. What it does is it puts the name underneath your drone as it's flying around. Now, the only thing about this is the simulator is built in such a way that if one of your drones is named Polaris, the camera is going to follow that drone. and then any other drones that you happen to have, because in future versions of this, you're going to have multiple drones. Your camera can't follow all of them at once. So whichever one is called Polaris, the camera is going to be by that one, even though your other drones are flying around the world. So this is mostly about just visualizing and kind of for fun. So you can name it whatever you want. Get company name. This is a method that the simulator calls on your class to find out what your team or company name is. And this is what's used down in the bar chart at the bottom to describe progress. So you can name your company whatever you'd like, and that'll show up. All right, and then this is really the intellectual heart of the exercise. This is one of the particular methods that happens during the life cycle of the drone. When I say the life cycle of the drone, what I'm referring to is the process of it picking up ninjas, ascending, transiting, descending, recharging, disembarking ninjas, embarking ninjas, taking off if it has someplace to go. And then if it doesn't have anywhere to go, and what that means is that it has gone everywhere that you've told it to go, then it goes into this drone idling state, and it gives you the opportunity to update the code. So this is a really natural place to put some controls, because what it means is that whatever things you've told the simulator you want your drone to do, they're all done now, and your drone has nothing to do. So what this code is doing is, first of all, it's calling the super class as drone idling, and we can look at that if we want. I'm going to use a F3 to jump to that definition immediately, which is in the parent drone controller. And you can see that the only thing that happens here is that the parent just says that drone idling was called. So it's just an output to the console indicating that the method was called. It doesn't actually do much other than that. So by virtue of your drone controller calling the superclass, all that's going to do is send out a message on the console saying that this event fired. And so you can see that in the console if you want. But now we're going to do some work. So what we're now going to do is we're going to ask the simulator to get all places. And actually, why don't we do this live so that we're not just talking abstractly. So what I'm going to do is I'm going to run this. I'm going to run it in debug mode, and we're going to stop here, and we're going to look at the different components. So I put a debug marker here by double clicking next to 54. And now I'm going to right click on the project name and go under debug as, not run as or coverage as, debug as a Java application. I'll go through the normal JMonkey setup, save any files that need to be saved. I'll be asked which class I want to run the main method of. I want to run the simulator class's main method. Hit OK, save all my files. JMonkey engine will ask how big of a screen I want, if all goes well. Wait for it. Wait for it. There it is. That's a new one. So this is saying open JDK cannot be opened because the developer cannot be verified. Verify that this app is not malware. Well, I don't care. I want to keep running. Well, that's no good. So that was an unexpected error, and I'm just going to walk you through my process of how I'm going to go about fixing that in case you encounter it. So the first thing I know is that by looking at that error, what Mac is telling me is that the Java virtual machine has not been approved by Mac in order to run on my computer. So when I tried to launch my program and the virtual machine tried to run, the Mac operating system intervened and said, this hasn't been appropriately signed by Apple, and so we will not run it because it could be malware. Generally speaking, I like that. In particular, at this moment, I wish it hadn't happened because it's screwing up my class. All right, so I'm going to come over here and I'm going to go into my properties and my Java build path where I specify which one I'm using. And I see that I actually have my JRE system library under module path. That always screws me up. So I'm going to take that and I'm going to remove it from the module path. I'm going to select class path. I'm going to add my library, add my JRE system library. I'm going to add the one that I've always been adding, adopt OpenJDK 11, finish. It's now listed under class path instead of module path, which always seems to fix a host of problems. Perhaps it will fix this problem. Apply and close. I'm looking down here to see if anything's building. Nothing is building, so it's probably good to go. Let's try and do that again. Go under debug as, Java application. Everything cleans up. Which main method do I want to run? I want to run simulator. Okay. All the files are saved. Wait for it. Boom. Great. Okay. So continue running JMonkey engine. We're going to launch our simulation. What's happening right now is the models are being loaded up. It's running fine. It's just in the background, right? And what happened is that the program is halted right now. It is in debug mode. Now I happen to have separated out the simulator from the visualization because I'm an awesome software architect. And so what that means is that the visualizer is still running. It's still running in full speed. So you see all the animations, you see the mouse works, that kind of stuff. But what's not happening is the controller or the simulator is not running, just the visualizer. The simulator is paused in my method because the simulator called drone idling on my drone here, and I have a debug breakpoint set there. And so everything is waiting for the debug process in Eclipse to let the program keep running. So I swing over here and I can see that the break is on line 54, and I'm interested in looking at the different components. So I'm going to switch to my debug view by coming up here and selecting debug and hitting open. And the reason why I want that is because I want to see some of the results of these method calls. I heard someone typing, so I'm going to double check, make sure there's no questions. Looks good. Okay, and back to code. So I'm going to step over this line of code. I'm going to use, yeah, okay. I'm going to do this so that you can see what I'm doing. Step over, boom. I now have a new variable in my live code called set of places. You can see that there are 10 different entries in set of places. And if I want to dig down in the variable explorer over here, I can see that place number 9 has the name Winter Hall. I can look at the position. I can dig into the position. I can see what its height is and what its latitude and longitude is. I can see if there are any ninjas that are waiting to embark. That's a linked list. It doesn't look like there are. So let's look at number 8. That's Trader Joe's. Is there anyone waiting to embark there? Nope. 7 is the showgrounds. Anyone waiting to embark there? Yes, there is one person waiting to embark there. And it is, this is position 0 in the linked list. This is all the information about the person. The person's name is Morgan Braze. You can see the person's position. You can see where the person starts. You can see where the person wants to go by looking at destination. They want to go to SBCC. So that's all information that you can look at live in the variables, but you can also, and in the code, you're going to have to look at it programmatically by calling methods. So let's go back to the code. Line 57, we have a current place, and we're going to get the destination. So when your drone is idling, it has already arrived where it wants to go, and it's sitting there waiting to be told where to go next. And so when we get the destination, let me step over this line, you can see that current place is going to be set equal to where the drone currently is. And the drone currently is at in and out. And you can see that that's consistent with what you see in the visualization. The blue box, which is the low resolution version of the drone, is at in and out. It looks like we got 2 people, Taylor someone and Sam someone, waiting at the in and out. All right, so now this set of all places that are in the world contains 10 different places. And what I want to do is from that set of places, I want to remove the place I'm currently at because I'm not interested in sending the drone to in and out because that's where I am. So let's take a look at set of places. Let's collapse some of these accordions. All right, so it's got 10 places in it. I'm going to step over this line and you can see that the linked list removed one element, the 9th element, or probably the 9th element, which was in and out. No, the 9th element was Winter Hall. So whichever element was in and out got removed and everything got bumped back. And now I am interested in converting this set of places into a list of places because I want to work with them in an order. So I'm going to step over this, and this is just simply converting it from one data structure to another. And now in addition to a set of places, I have a list of places that also have 9 elements in it. And now I just do a check. Because I don't know the situation, generally speaking, that my drone is in, it's possible that there could be no other places in the world. So I'm just going to make sure that I have more than one place left. And from that, I'm going to pick out the first place as the place to go. So let me step over that. As I look at my list of places over here, I open 0. I see my first place is McDonald's. I'm going to step over that. You can see place to go becomes McDonald's. And now this is where I control my drone. The way that I announce or I provide the sort of steering wheel, or I provide my orders to the drone, the way I communicate my orders to this drone is I do 2 things. I call set drone manifest, where I say which drone's manifest am I setting. This is the one that I'm currently controlling, this drone. And where am I going to tell all my passengers I'm going? I'm telling them I'm going to go to McDonald's. so that if either of these ninjas intend to go to McDonald's, they will get on my drone. Now, this might not be the best way to do this because those ninjas might not want to go to McDonald's. Maybe it would be smarter to pick a place that the ninjas want to go. That's not what this algorithm is doing. All right, so I will tell all the ninjas this is where I want to go by setting my manifest, and now I will actually send the drone there. And that's done by saying set the drone and the place to go. Now I'm going to hit run after this, and what's going to happen is I'm going to return from drone idling, and the life cycle of the drone is going to continue. The drone's going to go up, it's going to transit, it's going to go down, and I'm not going to see this method called again until it has landed at McDonald's and it is idle. So here we go. Running. There it goes. That happened fast, right? It lifted off, it took off from In-N-Out, and it went over to McDonald's. And so now I'm at McDonald's, and drone idling has been called again because the drone landed, it's recharged, everyone's gotten on, everyone's gotten off, and there's no place left to go. And as I walk through these different locations, my current place is no longer In-N-Out. My current place is now McDonald's. So now I'm going to remove a set of places. I'm going to turn that into a list. I'm going to make sure there's elements in it. Now I'm going to pick where to go. My place to go is to go back to In-N-Out. And so I'm going to set my manifest to there. Any ninjas that want to go there are going to go there. And then I'm going to route my drone, and then I'm going to hit play. Whoosh, that happened really fast. That's one of the reasons why you might not want speed at 100. All right, so now I'm paused again, and maybe what you can see here is that all this code is ever going to do is just go back and forth between In-N-Out and McDonald's. So that's not going to work out really well. So, maybe a better thing to do, the most simple thing to do, would be rather than picking my place to go as being the 0th element of my list, what if I picked a random place in my list? Well, that would be an improvement. I would at least go to other places. And if any ninjas happen to want to go there, they would get on board and I would go there. And so my drone would then bounce around the world. And that would be a really basic next step in improving the algorithm, because then you would see that your drone would bounce all over the place. What would be another reasonable thing to do? Well, rather than picking something randomly, why don't you look to see where the ninjas that are at your current location want to go and pick one of those locations. And then the ninja will get on board and you'll deliver a ninja. So that could be a pretty basic way to go. All right, I want to stop there. I don't want to take too much time on this, but I just wanted to, with hindsight, knowing a little bit better, or with a little bit of experience and looking at the code and having the chance to let this sink in a little bit, I wanted to give you an opportunity to sort of revisit this and understand what's happening. I also wanted to demonstrate how you can use breakpoints to understand what's going on with a little bit more clarity, so that you have some hope of being able to make sense of your drone controller in the rest of this ecosystem. I'm going to stop this. I'm going to open it up for questions. And while we're doing that, I'm going to try and do Sarah's sharing with the rest of y'all. So if you have any questions, go ahead and I'll do some administration here while we're waiting. All right, just added everyone left over on Saros. Going to watch the progress there. If I can get that window to show up again. It seems to be missing all of a sudden. Maybe we won't watch progress. And I'll try and set some folks to read only, if it'll let me. That's not letting me yet. Okay, I would like to be able to see progress. So I'm going to go under Window and Show View and Progress. There we go. No questions about Drone World. All right, well, just as you're thinking about this, the future assignments, you're going to have more than one drone to control. And you're also going to have to start paying attention to your charge. All right, while these settle out, let me open up Let me see, what have I got going on here? All right. Oh, I see what's going on. I've got two windows open. All right. Okay, what I would like to start with is by what we are talking about today is recursion, chapter 13. And I do want to make clear that the fact that we're talking about recursion at the same time we're doing drone world doesn't mean, I don't want you to take that to mean that I expect you to use recursion in drone world. In fact, I haven't really seen anyone use recursion in drone world. I don't recall anyone using recursion in drone world. So the fact that we're talking about these two topics is incidental. It's not implied to be some sort of like suggestion that you should use recursion in drone world. You can if you want, but they just happen to be the two things that we're covering at the same time. All right, so to do that, let's see. I want to open up the class that we're sharing today, and I want to start with a recursive algorithm here that maybe will make sense to you in the context of sort of things that you're familiar with in everyday life. So let me make a new package, and I'll call it File Finder. And what we're going to do is we're going to just write a short recursive program that goes through and tries to find all of the files on your hard drive that have a particular signature, have a particular extension. And so to do that, what we're going to do is, I'm kind of doing this on the fly, so we're going to create a new class, and we're going to call it File Finder Demo, and that will have a main method in it. Boom. All right, and we are going to, in that file, we're going to rely on a method that we haven't created yet. And we're going to, which is going to be called find, and in fact, we're going to call it file finder.find. Okay, great. All right, and so we're going to use a Java object called file, which is a representation of a file on your hard drive. And we are going, it actually can be a representation of a file or a folder, or or another name for folder is the directory. So we're going to use a constructor, and we're going to create a new file, and I'm going to actually name a directory. So this is my home directory on my computer. If you're on Windows, you're going to have to do something slightly different. You'll have to do a name that's something like C:\, the other slash. I think, I don't know if anyone can throw it into chat. How do you go from the root of Windows down to your user directory? Is it something like, I can't remember off the top of my head. It's something like documents DJP3. Anyone know off the top of their head? I could look it up in my virtual machine if not. Okay, anyway, it's going to be slightly different. This is a Macintosh specific file name. And then what we're going to do is we're going to say, hey, I want to find all of the files that end in .java starting at my starting directory, which I just specified right there. And this is something that we're going to implement. We're going to implement that using recursion. So let me have Eclipse create this for me. Okay, that looks good. All right, and I know that what I need here is I need my method, which is going to be called find. And the way it's going to work is that I'm going to print out all the files whose name ends in a given extension. Now, your file system is very explicitly a recursive sort of system because each folder has folders within it till you get down to files, and files are the end of your recursion. So any good recursive solution has kind of two concepts to it. It has an ending condition, and so our ending condition is when we reach a file, and it also has a way of making your problem smaller. And so in our case, the way we're going to make our problem smaller is by going deeper into the file hierarchy, because we know at some point we'll get to the end there. All right, so we're going to do a couple things to check that. So the first thing that we're going to do is we're going to try and decide whether or not the thing that we're being passed in is a directory. So if a file is a directory. That's just a method that's part of the file class. So we can just ask, hey, is this Java thing, is it a directory? And if it is, we know we have to recurse. We know we need to make the problem smaller. But if it's not, we're at a file, and that means that we're actually at the ending condition. So we're actually going to start with the else here. And I'll just put a note in here that says stop the recursion madness. All right, so what we're going to get from this then is we've just found out that this abstract idea of a file is not a directory, therefore it must be a file. And we're going to extract what the name of that file is by calling the method which says, get me the name of this file, a file.toString. That's how we do that, and we can hover over this to see the documentation for it if we want. And then we're going to check, now that we have the file name as a string, we're going to ask, does the file name end with the extension we're looking for? If it does, then we're going to print out the file name. If it doesn't, then we're not going to do anything, because the only thing that we care about here is whether or not is finding the files that have that extension. Let me just do the admin here. I don't know why it's not letting me put people in read-only mode. Okay, it's not letting me put people in read-only mode, so just please don't edit the code while I'm writing it. Okay, but if it is a directory, then we need to do the recursion. All right, so what we're going to do is we're going to repeat this exact same pattern, this find pattern, but we're going to repeat it on all the children. So let's get all the children for starters. So we can ask a file, if it is a directory, to give us all of the files that are within that directory. And what this will do is it will return an array of file objects, and we're going to call it children. That's just what we're going to call it. And we're going to say if children is not equal to null, it would be equal to null if this was a directory that had no files or other directories in it. So as long as there's something here, what we're going to do is we're going to loop through all of them using fast enumeration. So remember that what this is doing is it's taking an array on the right side of the colon, and it's doing a loop in which each time through the loop, the child variable is set equal to the next element in children. Children is an array of files. Each time we go through, we're going to pull one file out called child, and we're going to be able to work with it. And specifically, what we want to do is we just want to do the recursive process on that particular child. So this is the recursive call. We're going to find child, and we're going to look for the same extension. Save that. That's okay. I'm a little bit worried because I'm not getting the, this isn't changing the color of the text the way I expect the color of the text to be changed. So right now I'm expecting find to be italicized, and I'm expecting child and extension to be tan like it is everywhere else, and I'm not quite sure what's wrong that it isn't identifying it that way. Let me see if maybe if I just save it, that'll do it. No, I've got some kind of error. Oh, I've got too many close brackets. There we go. There we go. Okay, great. So the formatting shifted to what I expected. Italic because it's a static method, and then the variables are color-coded. So now we have lines 20 to 22. That's making the problem smaller. It is the recursive call on a smaller problem, which is trying to find something in a child directory. And then 24 to 29 is where we end the recursion. We check to see if we have, when we know we have a file, we check to see if it has the extension. So if we go back to File Finder Demo, like I have a lot of files under this. This is my home directory, so I have a ton of files. So I'm gonna have to stop this in the middle, but let's run it for the time being. I'm gonna run it as a Java application, and we'll hit OK. And then down in the console, why don't I see the console? What's going on? Show view console. There we go. All right, and you can see that what's happening is it's recursively going through my hard drive. It's looking in every single directory and every subdirectory, and it's looking at every single file. And if it gets to a file, not a directory or a folder, if it ends in Java, it's printing it out to the command line. And you can see I have tons and tons of code on my computer, so it's doing that. Now this is going to go on forever because my hard drive's large and I have a lot of code. So I'm going to pause it, stop it actually, and I'm just going to change it. I'm going to say, hey, what I want to do is I want to find all the, I don't know, docx files on my computer, which is a version of Microsoft Word. And so now the same search is going to happen, but instead of filtering at the end for .java, we're going to filter at the end for Word documents. I have far fewer Word documents on my computer, and it just, actually I might not have any show up. I mean, there are docx files on my computer, but it might just take forever to track down one. Give it 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, sorry, too slow. I don't have time for you. Life goes on. This is an example of a kind of recursive solution that isn't quite as much of a toy problem from what you might have been seen recursion used before. Like, for example, when we talk about the triangle problem, we talked about that with Dr. Lee. Perfectly good pedagogical way to introduce recursion. It's in our textbook. Makes total sense to get our heads around how recursion works. But then when we want to actually use recursion, well, the problems start to look a little bit different. And this is a good example of one. What I'd like to introduce to you now is a slightly different problem, and this is called the 8 queens problem. This is somewhere between a toy problem and a real problem. It's solving a mathematical problem in a way, but using a technique called backtracking. And I'm going to introduce the idea of backtracking because backtracking is how we're going to solve a Sudoku puzzle on Monday. We're going to create a more sophisticated version of a backtracking algorithm that solves a kind of more common problem than the 8 queens problem, which is Sudoku, which is kind of like a numeric crossword puzzle if you've never done one before. So let me introduce the idea of backtracking first using some slides. And the thing to know is that backtracking is a general way of solving problems, but it has a very similar structure to the way we dig down in these files. Instead of digging down into a file structure, we're going to dig down into a set of solutions, possible answers to a chess problem. So let's start there. All right, so backtracking. Slides on the screen here. Backtracking is a particular approach to solving a problem. It is a hammer, and if your nail is the right shape, it's the right way to solve a problem. It's not the way to solve every problem, so I don't want to suggest that. But it is a very powerful problem-solving technique that relies on recursion. And the way it works is that as you build up your solution, you improve your solution step by step by step so that you get closer and closer and closer to a complete solution. For example, if you had a crossword puzzle, you might add one word and then another word and then another word until your crossword puzzle was completed with all of the words in the crossword. A partial solution to a crossword puzzle would be a crossword puzzle that only has a few words added to it. The most simple partial solution is a crossword puzzle that has nothing filled out. That's barely should be called a partial solution, but I guess it's the start of a partial solution. When you add one word to a crossword puzzle, now you have a little bit more of a solution. And eventually, if you keep adding on to your partial solution, you'll end up at your goal, which is a completely solved crossword puzzle, as an example. If at any point you have a partial solution, but it violates some rules or something, you throw it away and you don't continue walking down that path. And the other thing that you want to do instead is you throw away the possible solutions that can't be completed because they violated some rule, and instead you focus on those partial solutions that haven't violated rules yet. And you sort of create this tree structure of more and more solutions that are more and more specified until you get to a complete goal. So some particular properties of problems that are well suited to backtracking solutions. You have to be able to look at a partial solution to a problem and answer the question of, 1, is it still possible that this could end up being an actual solution? And if it isn't, then you need to be able to abandon it and don't look at any more specific versions of that problem. If it is possible that you could continue to extend it, then you can continue to extend it. So you have to be able to, at any given moment, look at a partial solution and say, this could be completed or it can't be completed because it's violated some rule at some point. You also have to have a way of improving your partial solution. So algorithmically, you have to have a partial solution, you have to be able to say it's good or it's bad, and you have to be able to take the next step towards a more specific answer, like adding another word to the crossword puzzle. The idea of a backtracking algorithm is that you're going to look down all possible paths abstractly for your solution, and if you ever get to a dead end, you're going to stop walking down that path, and you're going to go back to the last place that you had a good partial solution. You're going to go a different route instead, kind of like walking through a maze. If you get to a dead end, you're going to go back to your last decision point, and you're going to go right instead of left, because left went to your dead end. So you have to be able to do those things. Here's some pseudocode that describes the basic idea for a backtracking solution. The name of the method is solve. So you're trying to solve your problem. And what's passed into your solve method is a partially solved solution. Not a complete one, but partial one. First thing you need to do is you need to be able to examine that partial solution. And what examine needs to be able to tell you is it possible to complete it? Is it complete? Or should we reject it? So if that partial solution actually is complete, if it's accepted, then we print it out or we add it to a list of good solutions or whatever we want to do with the solved problem. That's what we do if it's accepted. Otherwise, if it can be completed and we're going to continue it, then we're going to extend the partial solution in any way we know how, all these different ways. We're going to branch out. We're going to take one solution. We're going to branch out all the possible next steps we could take, and we're going to try and solve each one of those in order. So that's that additional recursive call at the bottom. That call at the bottom, solve P, is a recursive attempt to solve the problem. The bottom one is like when we start going down subdirectories looking for Java files. For each P and extend partial solution is like when we look in each subdirectory for our Java files. All right, so let's apply this to a particular problem. So this problem is a variant of a chess problem, and the chess problem is called the 8 queens problem. It's generally called the n queens problem, the letter n, but this is called the 8 queens problem because we're trying to solve it on a board that's 8 by 8. You could solve it on a board that's n by n generally. So the problem is to try and place 8 queens on the chessboard so that none of them attack any of the other queens according to the rules of chess. And if you're not familiar with the rules of chess, what it means to attack another queen is it means that a queen can attack another queen if they are on the same row, or if they are on the same column, or if they are on the same diagonal. So if you look at this particular solution to the 8 queens problem, what you see is that each of those queens are placed in such a position that none of them are on the same row, none of them are on the same column, and none of them are on the same diagonal, like an X pattern. And so that's a solution to the 8 queens problem. There are more than one solution to the 8 queens problem, but our goal is to try and find solutions to n queens problem or 8 queens problem in specific. So the way we do this using that pattern that we just looked at was we're going to have a chessboard and we're going to examine a partial solution. And if our partial solution has 2 queens that attack each other, we're going to reject it. If it has 8 queens, then we're going to accept it because it's a solution. Otherwise, we're going to try and put another queen on the board, and then we're going to recurse on that new partial solution. The way we're going to put another queen on the board, that's extending the partial solution. And we're not going to think too deeply about it. What we're going to do is we're just going to put another queen on any empty square and all of the other empty squares. And then we're just going to check to see if we did it badly and whether they attack each other. And if so, we're just going to call that a dead end and we're not going to explore it anymore. And so just for efficiency, we're just going to extend this row by row by row to do this in a way that's kind of clever. All right, so let's take a look at this, and let's start with I'm going to drop it in the code, and I'm going to make a new package for us, and we'll call it n queens, although we're actually going to be solving the 8 queens problem. And the first thing that I want to do is I want to introduce the idea of a queen object. So let's make a new class, and we'll call it a queen. And so this is going to be just a queen placed on a position on the chessboard. That looks good. That looks good. All right. And I've got a little bit of code ready to go here because time is short. All right. So let's take a look at what we've got here. What happened? I don't know about that. All right, so we've got a class queen. It has 2 instance variables, the row it is on and the column it is on. We'll use numbers 0 through 7 in order to represent the 8 positions. When we construct our queen, we just say which position it's at, row and column. And then we have 2 helper methods, one which is a method that returns true or false. Does this queen attack the other queen? We can figure that out pretty easily. If this queen's row is the same as the other queen's row, then it's an attack. Or if this queen's column is the other queen's column, then it's an attack, or if it's on the same diagonal. Now, this is a clever way of telling whether it's on the same diagonal or not. It says that if the difference between the rows is equal to the difference between the columns, taking the absolute value of it, this means that it's on the same diagonal. You can explore that a little bit to convince yourself that that's correct. And then finally, we're going to have a toString method, and this is just going to convert the columns into a letter so that we're not confused about what is a row and what is a column. Since we're using internally, we're going to use integers, but when we print it out, we're going to print out the letters so that we have a pattern that looks like, where's our screen here, so that we have a pattern that looks like this with A, B, C, D, E, F, G, H at the top for columns. All right, so that's our queen. That's the first thing that we need. The next thing that I want to add is I want to add the idea of a partial solution. All right, so let's make our partial solution. And we're gonna, man, we're working against the clock today. I want to knock it out though. All right, let's see. I'm gonna drop a bunch of code on you. All right. So our partial solution is a chessboard. A partial solution is a representation of a chessboard. That chessboard has a certain number of queens that it's keeping track of. Ultimately, we hope it's going to be 8 queens. That's right here. We have a couple constants in here just so that we can speak abstractly about accepting, abandoning, and continue. So these are just types that we're going to use. When we construct a partial solution, what we're going to do is we're going to say, hey, if you have a partial solution with a board of 8 by 8, then what I'm going to need is I'm going to need an array of 8 queens because I'm going to need 8 queens on my 8 by 8 board. And so I'm just going to create some space to hold those particular queens. So that's all my constructor does. I have 2 methods, abstractly speaking. Let me collapse them because we're talking about them abstractly for starters. We need to be able to examine a board to tell whether or not it is valid. And we need to be able to extend our board in order to be able to be able to recurse on a slightly extended solution. So examine means we need to be able to look at a set of queens and say whether or not it is a good solution, whether or not it is a bad solution, and if it's good, then we can go ahead and continue, or no, whether it's a complete solution. So accept means it's a complete solution, abandon means it's a bad solution, and continue means we need to do more work to fill out the queens. So let's look at what that looks like. We need to determine which of the states our current board is in. Okay, so we're going to look at each one of the queens that we're keeping track of in our partial solution. And we're going to compare it to every other one of the queens that's in our partial solution. So our first one will be comparing 0 to 1, and then 0 to 2, and then 0 to 3, and 0 to 4, and 0 to 5. Then we'll look at 1, 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, and then 2, 2 to 3, 2 to 4, 2 to 5, 2 to 6. That's what these 2 loops do, these nested loops. If any of those pairs shows that one of those queens is attacking the other one, then we abandon this solution because it can't be completed. If after evaluating all pairs of queens, none of them are attacking each other, that's a pretty good position to be in. In which case we ask, do we have 8 queens? If we do, then we have a solution. Because we have 8 queens, none of them attack each other, we're done. Otherwise, accept. Otherwise, our examination will say, well, you have a valid solution so far, but you need to continue because you haven't added enough queens. All right, before we look at extend, let me show you the wrapper that's going to run our pseudocode, and then this will be it. All right, so we'll call it n queens. All right, and in n queens, we're going to have our main method that does our work for us. All right, so what's our main method going to do? It's going to attempt to solve a partial solution that has no queens on it. All right, so that's our starting point. We're going to add queens one by one till we get to 8. Solve is a method that we need to add here. What solve is going to do is it's going to take our partial solution It's going to examine it to see whether it is complete, whether it needs to be abandoned, or whether it needs to be continued. If it turns out that our partial solution is complete, then we're going to print out the solution. Great. If it turns out that our solution is good but not complete, we're going to step by step go through all the possible extensions to our board and recursively solve them, just like we did when we were searching through our file hierarchy for Java files. And that's it at the high level. So the only thing I haven't showed you how to do is how to extend these solutions. And let's see, what do we do here? Is that right? So let's take a look. I'm not sure what's going on there. What's happening? Never used. Okay, well, let's get rid of it then. That's making me nervous, but okay. So to extend our solution, we open this up and we say, all right, well, we need to take our partial solution and we need to create a bunch of extensions. So here's a list of all of the ways in which we could extend our potential result. Each time we're going to extend it by one row, and so we need to add 8 new possible extensions to our board. We will take one of these possible extensions and we will create a new board. So this is actually branching out in tree structure. We'll copy over the partial instruction, and then we're going to add one more queen to our board. We're going to return all of these partial extensions, and then the code above us will go through and evaluate them one at a time. All that to say, when we run our main method, and we solve it, what gets printed out to the console is all of the possible n queen solutions. So these are all the possible configurations of places where you could place a queen so that they don't attack each other. You put one on H1, one on D2, one on A3, one on C4, one on F5, one on B6, one on G7, and one on E8. And this will solve that particular problem. All right, we're out of time, so I won't elaborate on this anymore. You should have this code now available to you. Can you just validate, tell me in game that came over Saros for you? Give me a little chat to convince me that it worked okay. Okay, so some people didn't get it well, and I will stick around in a moment to reshare it with anyone that needs it. Did anyone successfully get it? Huh. Okay, Trent got it. Okay, great. All right, if you successfully got the code, then you should be able to run the 8 queens problem, and you can disconnect, and you can thank you for your attention today. On Monday, come ready to code along with me. I'm going to have a sequence of 8 videos that you can follow along with in order to build a Sudoku solver. Sudoku is like a mathematical crossword puzzle. We're just out of time. I'm sorry. Thank you for your attention. Stick around if you want me to share the code. I appreciate your patience. Have a great day. Have a great weekend. God be with you. Peace. All right, and let me shut down YouTube, and then I will go in game and we can fix this up. Okay, so wrapping up the YouTube broadcast. This is April 9th, Friday, CS-030. Today we're talking about recursion, backtracking. In the beginning, we had an intro to our drone world. Thank you for your attention. YouTube, we will see you in the future.